Hello everyone. In this video we will look at the oracle complexity of mirror descent for various cases involving convex functions. Let us begin with a quick recap. Recall that we are solving the problem x star equal to argmin over x in calligraphic x, f of x. For convex f, we will first consider f that is Lipschitz continuous, so that the dual norm of its subgradient is less than equal to LF. The mirror descent updates are equivalent to the following equations. Gradient of phi y of t plus 1 equal to gradient of phi xt minus eta t gt. Xt plus 1 equal to px phi of yt plus 1, which is equal to argmin over u in calligraphic x d phi of u comma yt plus 1. Where phi is strongly convex, so that d phi of x comma y is less than equal to 1 by 2 mu phi dual norm square of gradient phi of x minus gradient phi of y. And finally, the quasi non-expansiveness property, which said that d phi of z comma px phi of x is less than equal to d phi of z comma x for all z in calligraphic x. So we have written down all the properties that we need in order to derive the required result. Now we state the first oracle complexity result. Which is that for f convex and Lipschitz, the number of oracle calls in order to ensure that the best optimality gap is less than epsilon is given by order b lf square by mu phi epsilon square. For step size eta equal to mu phi epsilon by lf square, and order b lf square by mu phi epsilon square log 1 by epsilon for step size eta t equal to square root of 2b mu phi divided by lf square small t, where b is such that d phi of x star comma x1 is less than equal to b. Observe here that the result generalizes the oracle complexity result we obtained earlier for subgradient descent. In fact, if you remember, if we take phi equal to half norm of x square, then the result will be exactly the same. In fact, the only difference between the two results is the additional parameter mu phi in the denominator, and it will be 1 if we choose phi equal to half norm of x square. The proof is also similar to subgradient descent in overall structure. In fact, we will use the same recursion that dictates the choice of the step size. The only difference is in the derivation of the one-step inequality, which will now require us to use the generalized Pythagorean instead of the expansion of the norm square. So unlike the subgradient method, here we need to bound d phi of x star comma xt plus 1 minus d phi of x star comma xt, so that a telescopic sum can be carried out. Now, since xt plus 1 is equal to px phi of yt plus 1, the quasi non-expansiveness property says that d phi of x star comma xt plus 1 is less than equal to d phi of x star comma yt plus 1. So substituting this, we obtain that d phi of x star comma xt plus 1 minus d phi of x star comma xt is less than equal to d phi of x star comma yt plus 1 minus d phi of x star comma xt. So now let us expand the right hand side to see that it is equal to inner product of gradient phi yt plus 1 minus gradient phi xt comma xt minus x star plus d phi of xt comma yt plus 1. Now we need to bound the first and second terms individually. So let us carry it over. The first term can be bounded using the update equation and the convexity of f, which yields that inner product of gradient phi yt plus 1 minus gradient phi xt comma xt minus x star is equal to minus eta t times inner product of gt comma xt minus x star, which is less than equal to minus eta t times f of xt minus f of x star. The second term can be bounded using the strong convexity of phi, which implies that d phi of xt comma yt plus 1 is less than equal to 1 by 2 mu phi times dual norm square of gradient phi xt minus gradient phi yt plus 1, which can be written as eta t square by 2 mu phi times dual norm square of gt. So where we have used the update equation. Since f is Lipschitz, the last term can be bounded by Lf square. So we obtain that this is less than equal to eta t square Lf square divided by 2 mu phi. So combining these two inequalities and rearranging, we obtain that the required one-step inequality is eta t f of xt minus f of x star less than equal to d phi of x star comma xt minus d phi of x star comma xt plus 1 plus eta t square Lf square by 2 mu phi. The rest of the proof is now very similar to what we had in the case of subgradient descent. Taking the telescopic sum over t, we obtain that summation over t from 1 to capital T, eta t times f of xt minus f of x star is less than equal to d phi x star comma x1 minus d phi x star comma x of capital T plus 1 plus Lf square by 2 mu phi summation from t equal to 1 to capital T eta t square. So we can bound the first term on the right by b and then drop the second term, and we can also lower bound the right hand side with the best optimality gap, so that we obtain the f best of t minus f of x star is less than equal to b plus Lf square by 2 mu phi summation of eta t square divided by summation of eta t. So as in the subgradient case, there are two ways to select eta t. We know epsilon in advance, then we can set eta t equal to mu phi epsilon by Lf square, and in which case the bound will be t equal to order b Lf square by mu phi into epsilon square. Likewise, if we set eta t as square root of 2b mu phi by Lf square t, then if you recall, summation of eta t will be square root t and summation of eta t square will be log of t. So we will obtain the oracle complexity bound as order of b Lf square by mu phi epsilon square log 1 by epsilon. So here I have skipped many steps, but you can have a look at the subgradient proof to see the intermediate steps. These are exactly the same. The following example demonstrates the difference between projected gradient descent and mirror descent. Suppose that we are interested in minimizing a function f whose subgradient has bounded entries. That is, the ith entry of the subgradient is less than equal to 1. And the optimization variable is a PMF defined over the probability simplex. Suppose we use projected subgradient descent to solve it. Then since the L2 norm of the subgradient is less than equal to square root n, oracle complexity of projected subgradient descent will be order b square root n by epsilon square, which is increasing in n, even if b is a small constant. On the other hand, if we use mirror descent to solve, then we will end up using the infinity norm of the subgradient, which is less than equal to 1. So mu phi equal to 1, since the negative entropy, if you recall, is 1 strongly convex with respect to the L1 norm. So the oracle complexity of mirror descent will be order b by epsilon square, which does not depend on n if b is a constant. Now even if we start at x1 equal to the vector with entries 1 over n, then it can be seen that d phi of x star comma x1 is equal to sum over I x log nx. which is less than equal to log of n for any choice of x. So the oracle complexity is still order log n by epsilon square, which is only logarithmically increasing in n, resulting in a much better overall oracle complexity. We have seen the performance of the mirror descent for non-smooth cases. In the next video, we will analyze the performance of mirror descent for smooth and strongly convex functions.